Hello and welcome. Good morning, good evening, good afternoon, depending on where you are. And welcome to the session Optimizing Your Workload on Azure SQL Database. My name is Sanjay Mishra, and I'm here with two of my colleagues, Denzil Ribeiro and Dimitri Furman. And we are from the Azure SQL product team. And together we are going to walk you through various examples on how you can optimize your workload on Azure SQL Database. Azure SQL Database can run a variety of workloads, and this session will showcase you through demos how do you optimize them. We'll start with a brief overview of the platform. Then we'll go through various examples on optimizing network traffic, optimizing storage, optimizing CPU utilization, and we'll also show you how to optimize efficient data loading into Azure SQL. And everything will be shown through demos so that you can relate practically to your real life situations. Rest of the session today actually assumes that you know a bit about Azure SQL Database, how these databases are various service tiers are offered, how we provide high availability, how we provide security. If you're not familiar with Azure SQL Database, I encourage you to look into this free video that we have published on YouTube. The link is at the top, Azure SQL Bootcamp, and you may like to go through them. And in a month's time, these two books will come out. You may like to grab one of these books. These videos were created by the authors of these two books, so you'll find them very useful. A brief overview of the Azure SQL family of products. We have platform as a service and we have infrastructure as a service, depending on whether you want to manage your own VMs and other infrastructure, or you want Microsoft to manage your database and give you database as a service. For platform as a service, we offer a database model and an instance model. And for infrastructure as a service, we provide you a VM. Irrespective of which one of these you choose, you get the database that is based on SQL Server. That is an industry-leading security, compliance, price performance, and a database which is the least vulnerability across the industry. And among the choices, which service to choose when? My co-author Anna will go through a session. It's called Azure SQL What to Use When, and I encourage you to attend that session to understand how to choose your service. The rest of the session is based on Azure SQL Database. The demos will be based on Azure SQL Database, but the tips and techniques that we showcase will be applicable to managed instance as well as VMs as well. So how Azure SQL has evolved over the years. It was introduced in 2009, and at that time it used to be a 10 gigabyte per database limit. Over the years, the size has grown from 10 gigabytes to 100 terabytes in 10 years time frame. It has also improved in terms of scale, performance, functionality, security, high availability, and all those factors. It's a very mature product today, runs some of the most business critical application in the world. It has become the go-to database for various type of workloads running in cloud. When we talk about database workload, there is actually a spectrum of database workload. Not two workloads are alike. There is diversity in those workloads. On one extreme, you have a set of workloads which are very short transactions or queries which require high concurrency, fast response time, require high availability, and there you are actually optimizing for lowest possible latency. On the other extreme, you have database workloads which are you are doing bulk operations on huge data sets. You probably running a very complex queries. There you need good performance and scale, but your main goal is optimizing for high throughput. So real world workloads are combination of all these. They are somewhere in the middle of all these. Some veer towards the left, some veers towards the right, but you can understand that a workload may have multiple of those characteristics together. Azure SQL Database is a great choice if you have any generic OLTP workload. Azure SQL Database is fantastic for that, just like SQL Server. If you have a mixed OLTP workload and a reporting workload, which is also known as an hybrid transaction and analytics processing workloads, HTAP, Azure SQL has tons of great capabilities to be able to make you successful on those workloads. Data marts, Azure SQL DB is a great choice. High concurrency, low latency workloads such as gaming workloads, IoT workloads, trading workloads, stock trading application, they are very good on Azure SQL Database. And any data, in general, any database workload that runs on an SMP relational database, whether it is run on on-prem or any other data center, if it is running on SQL Server or a similar relational database, and you're looking for a platform as a service, database as a service in cloud, Azure SQL Database is your choice. Here are some examples of customer case studies that we have published, and you can read the customer stories and how they use Azure SQL Database. You'll be able to gain some insights into this. And as you can see here, we have from SaaS applications to online gamings to financial applications to graph processing. We have a wide spectrum of workloads. And not to mention, Microsoft's Bing Ads runs on Azure SQL DB. So as Dynamics 365 and SharePoint online applications. With that, let's take a look at a demo. In this demo, I'm going to showcase how to scale an IoT workload on Azure SQL Database. IoT workloads, as we mentioned before, require very low latency, high concurrency, and and lots of concurrent insertions per second. And what I'm showing here is actually a map with power meters. The power meters are installed in residences, in businesses, and these are smart meters. They take the reading themselves, and they're capable of sending the meter readings to a central database. And this database we're going to showcase how many of these meter reading insertions I'm able to handle in a database. So on my demo machine, basically I have completely cleaned the database. There is nothing, no data on this database. We're going to start a workload. We're going to start inserting. And to start the workload, I have a console application which I'm going to kick off, and then you can see the progress. As you can see, very quickly the database ramps up, and we are almost at 3 million rows being inserted per second. And to showcase that these are actually going into the database, let's query these tables, and you'll see that that data is actually landing in this database. Here you see there are millions and millions of rows have already come into the database. And now what we're going to discuss is how we are able to manage such a high concurrent, high throughput insertion per second from a thousands of such devices coming together. What we have done is in this database, I have two sets of tables. One table where the insertion is actually coming from these devices is a memory optimized table. And as you know, in SQL Server, in Azure SQL Database, you can create memory optimized table, and this table has been created with durability equal to schema only. And this allows very fast insertion, no locking, no latching, and very extremely low latency. And thereby we're able to generate or capture so many insertions per second. While this is happening, memory is limited. So we ultimately want to take this data from the memory optimized table and put it in a durable table. And that durable table is defined with a clustered column store index, which provides very high performance for querying. It's a very highly optimized storage for storing the readings for the future. What you would like to do is that while this workload is going on, you may actually want to query the data as well, which is great. You can query the data. To query the data, you can go to Management Studio. Let's check how uh, our performance is going on here. This the resources on this machine, as you can see, almost pushing hard. They're going 93%. Therefore, I think we do not have much CPU headroom on this database to run any query. But no worries, because this is a business critical tier, SQL Database, we offer you a free read replica. The free read replica is actually similar to a always on read replica that you use on premises. And this free read replica can be used to run a read workload. I'm going to run a read workload very similar to my write workload, and this read workload is going to run hundreds of queries, thousands of queries on this read replica database. And let's see how this goes. As you can see, thousands and thousands of rows are being returned from, while insertion at a very high rate is going on the primary. The secondary is able to serve the queries at a significantly high rate as well. So this showcases how an IoT workload where you need to ingest data very fast with extremely low latency can be optimized in Azure SQL Database. And with that, I hand over to Dimitri, who will walk you through how to optimize network and storage and then move forward. Thank you.
Hello and welcome. My name is Dimitri Furman. I'm a program manager on the Azure SQL Database team, and I will continue our session to talk about network and storage best practices in Azure SQL Database. So talking about network latency first, cloud networks are special, and because of that, you will see very often round-trip network latency that is variable and typically higher than on premises. So what can we do to address this in our configuration of your Azure SQL Database? There are some best practices for latency sensitive applications. One is very simple, and that is to collocate the application in the database in the same region. That usually is the case for most applications. However, we still see some latency sensitive applications that talk cross-region and incur very high network latency, impacting the application performance. Then you can enable accelerated networking in the application tier. That's already available for most VM types in Azure. And accelerated networking is enabled in Azure SQL Database on Gen 5 hardware and later. So that will improve both network latency and network throughput. Then you should set connection policy at the logical server level to redirect. So there are two connection policy options we have. One is called proxy, that's the older option, and the newer option is called redirect, and that is what is recommended. With the proxy connection policy, when the client connects to the database, it first connects to a gateway. And the gateway is one of a set of machines, shared infrastructure across multiple tenants in a region that processes the login attempt and then starts proxying all traffic between the client and the node that hosts your database for the duration of that connection. So traffic goes back and forth through the gateway. Now, because that has an extra network hop, network latency is higher. In addition, because the gateway is shared infrastructure, if let's say you have some idle connections, they may be terminated after some period of inactivity just to keep the load on the database lower. Now, with the redirect connection policy, the connection flow is different. When the client connects to the gateway, that still happens for the very first login attempt. The gateway responds back to the client with the DNS name and port number of the actual instance on the node in a tenant ring that hosts your database. And from that point on that session, the client will always connect directly to that instance. So all traffic will flow back and forth bypassing the gateway. So just a single network hop and not really subject to connection termination as frequently as if the connection were through the gateway. Now, to use the redirect connection policy, make sure to have to use recent driver versions, because if you have a very old driver several years ago, it may not even support redirect, and then you will still go through proxy even if you enable the redirect connection policy. It's very easy to do to enable redirect. It's exposed in Portal now on the firewall configuration page. So in most cases, you should do this. There are some tools to measure network latency just to know, just to possibly compare it to your on-premises network. A very simple one is just to select to run a simple query in a loop. In that case, make sure to use a sufficient number of iterations in the loop, hundreds, because the very first one will take longer because of additional login processing. So to get an accurate number, you should do it a few hundred times. PSPing is a tool from sysinternals that lets you open a TCP connection to the gateway and measure latency between your client and the gateway. And then there are a couple of additional tools. Latte is a Windows tool. SuckPerf is a Linux tool that let you measure latency in Azure. So, what are the best practices in terms of application design? So there are basically two design goals to reduce network latency. We want to reduce the number of round trips, and we also want to reduce the amount of data on the wire. So the reasons are fairly obvious. Every round trip takes time, and it takes more time if there is more data to send or receive. So what does it mean? We want to do data processing in the database in most cases, so that there is less data flowing over the network. Now, that doesn't mean pushing business logic to the database. That, in most cases, would be an anti-pattern. But we want to use the database engine for things it does best, such as joining datasets, filtering, projecting, aggregating. So basically, everything that can be done in a set-based query should be done in the database. And more complex business logic, procedural business logic, should be done in the application. One dataset, one database call. What I mean by this is that if you have to send some data to the database, it's always better to send it in one call. So if, for example, you're inserting 100 rows rather than running a single row insert statement 100 times, use a table valued parameter with 100 rows. A table valued parameter is basically a type of parameter where you create a table type in the database with a specific schema, some columns. And then in the application, you create an instance of the table type, populate it with rows, and then send that one parameter as a single parameter with a single database call to the database. And that sends all of those 100 rows, for example. So that's the best approach to use if you have a tabular data set to send from the application to the database. If you have some kind of a document, hierarchical structure, you can use JSON or XML and just send that single JSON or XML value as a parameter, and then parse that in the database, or possibly just insert it as is. And then there is a very simple approach. If you, let's say, you have to send some primary key values to the database, you can just create a delimited string, send it to the database as a single value, and then use a string split function to create a table that you can reference in your queries to say insert those values or filter by those values and so on. If you have to send larger amounts of data to the database, some kind of a bulk load, SQL bulk load class is available in both .NET and JDBC. And we'll talk more about this later in our session. And finally, you can use a table value constructor, which is basically a way to construct a table using the values clause. So in this case, we have 3 rows in the table, and we insert those 3 rows into the database in a single statement. So again, avoiding chattiness, avoiding multiple round trips. And then the last two best practices are actually not new at all. They've been around probably for as long as SQL Server have been around. But they're still very relevant, so don't read unneeded data. Select star remains an anti-pattern, very much so in the cloud. And then using set and account on in the beginning of your batches will often avoid an extra round trip. Let's talk about storage latency. So in Azure SQL, we use 2 different storage types, remote storage, which is basically Azure Premium Storage, remote SSD, and local storage, so local SSD on the actual machine that hosts your database. So the latency numbers vary. Local storage has lower latency in general. The numbers you see here are not really something that happens that you will observe all the time, but that's what you typically observe, right? And then typically for smaller IO sizes, less than 64 kilobytes. As you probably know, SQL Server can issue IOs of very large sizes, sometimes up to 1 megabyte, maybe 4 megabytes if you're doing things like backup. So we are, with the latency numbers here, are typical for smaller IO sizes. And they are separated into read IO latency and log write. And why log write? Because that's what matters most when writing data to the database, when committing a transaction. So every transaction commit, as we can see, can take from 1 to 5 milliseconds. So the best practice that immediately follows is to avoid unnecessarily frequent commits. Let's say if you have to insert 10 rows in the database or update 10 rows, don't just do it 10 times. Either do it in a single statement, or if you have to do it 10 times because, let's say, you're running a loop, enclose it in a transaction. So in a transaction, there is only a single commit, so you will incur the overhead of storage log write latency only once when committing the transaction, as opposed to 10 times when inserting every row. So sometimes we get questions: what happens? Can you improve latency? Can you reduce it by scaling up the database? By allocating more cores? So the answer is not directly, because just because you've allocated more cores to the database, that does not change the type of storage. It still is a remote or local. However, it can impact latency indirectly by changing the resource governance limits on IOPS and throughput. So what happens, the way resource governance works, if you approach resource limits, say, let's say you have 1000 IOPS resource limit, and if you are at, let's say, 950, the resource governance in the database will start slowing down your IOs, so that you still they still complete, but they complete slower. So the latency of each IO becomes higher. So if you see some very high latency numbers, much higher than what you see in this table, that's probably because you're getting throttled by resource governance, and that applies to both IOPS and throughput. So in that case, your options are to increase the service tier, basically increase the limit, or modify the workload so just that it drives fewer IOPS or less throughput. And we'll talk more about this in just a minute. So our next topic is resource consumption and how you can optimize it. So before we talk about it, let's just define some terms. When we talk about resources here, I'm talking specifically about database resources. So things like CPU, memory, storage, and so on. I'm not talking about ARM resources or Azure resources or anything like that. So we have a concept known as the database service objective. It's actually known by many other names, such as compute size or slow, service level objective, and so on. And it's basically just an allocation of resources given to a database. So this allocation of resources is set aside and enforced using resource governance. And the reason we need this is to provide a balanced database as a service. So all of those things you expect from a PaaS service, such as high availability, disaster recovery, backup restore, predictable performance, multi-tenant fairness, and so on, all of those things are made possible by using resource governance, so that a single customer workload does not impact other customer workloads. And that lets us have a wide range of compute sizes, deployment options, from single database to elastic pool to managed instance, different hardware generations, and so on and so forth. So today, if you look at available service objectives, they range from basic in the DTU model with just 1/4 of a CPU core and 2 gigabytes, all the way up to a business critical M-series database with 128 cores and 4 terabytes of memory. All of that made possible by having a resource management tier that manages resource usage. So how can you optimize your resource usage, and not just usage but cost? And cost is very important here, because unlike on premises, where you basically have some hardware, physical or virtual, and it's already paid for, in Azure, in the cloud, you pay by the hour. So it's very important to optimize resource usage so you don't have to pay for more than you need. So let's say you have a performance problem. So the very first thing you should do is check resource usage. And that's actually quite simple to do. You can just look in the portal using graphical metrics, or you can look at DMVs. DMVs are sometimes preferred if you need to see the very up-to-date data. So there is some data latency with metrics you see in the portal, typically maybe 20 seconds or so. Whereas if you query the first DMV, DMDB resource stats, you will see data almost immediately. So very important to look at each resource type. And that's particularly important for DTU databases, because if you just look at DTU, you will know that you may be approaching your limits, but you won't know which particular resource is responsible for that. Is it CPU? Is it log write? Is it workers? Is it something else? So even though the default in the portal is to show you the DTU value, it's always a good idea to split that into different resource types and look at individual resource types so that you know what you should troubleshoot. Now, let's say there is a resource bottleneck. So you basically have two options. You can either tune the workload or you can scale up. So tuning obviously is preferred because then you can continue using your existing service objective without incurring extra cost. If you have to scale up, that remains an option. Uh, as I showed before, we have a very wide range of service objectives, but of course it will be at extra cost. So tuning is preferred. And how can you tune a workload? Well, that's a very broad topic that I can't really describe in great detail today, so I'll just outline some general approaches. So you can use query store to find the top resource consumers. You can use weight analysis. You can tune indexes, or you can rewrite code. So that's kind of covers probably 80 to 90% of things you would do to tune a workload. Now, we talked about what to do if resource usage is high, but what if it's low? So we actually find it sometimes that a customer would migrate to Azure using their on-premises configuration as a baseline. And then over time, they find that they have over-provisioned their database. So if that's your case, feel free to scale down because it's actually very easy to scale down and scale up as needed in Azure. So scaling down for over-provisioned databases is the best practice. All right, next, let's look at a demo. So in this demo, I will run a database workload against the database using a tool known as OSTRES from RML Utilities suite. So in this case, I'm executing a stored procedure called busy worker. And that's basically executed on 150 connections, and each connection will call that stored procedure many times. So let's do that. So immediately I see that I get some errors. So if we take a look at one, we see that the error is that we've exceeded the request limit for the database. So clearly we are hitting some resource limit. So let's see what it is and what we can do about this. I will just push this to the side so we can still see this happening. And I will open my management studio side by side. So I have some diagnostic and troubleshooting queries here, but the problem is when we are exceeding the request limit, I may not be able to even run those queries because we are actually out of workers. We are out of worker threads, so even attempting to connect to the database will require one worker thread, and I may not have any left in this database. So luckily, there is a solution, and the solution is something that has been available in SQL Server for quite some years, and it's known as a DAC, or Dedicated Administrator Connection. That's also available in Azure SQL. So if you connect to the database using this admin prefix, admin colon, and then following your database server name, that's one prerequisite to use DAC, and then the other one is to use the actual database instead of connecting to the master on the logical server. So this one is opposite to what you would do in traditional SQL Server, where you have to connect to master to use DAC. So let's go ahead and connect. So if I do that, I actually get an error. Now, so the error is it's actually, in this case, it does not matter. So what happens, we only support one DAC connection to each database in both SQL Server and Azure SQL. However, Management Studio will attempt to open multiple connections for each query window. So in this case, it did open a DAC connection successfully, but then the second connection failed open. So you can just click OK to ignore this. And if we run this query, we'll actually confirm that yes, indeed, we are having a DAC connection. So for our session to 82, which matches what we see in Management Studio here, we see a DAC group. So next, let's look at resource consumption. So clearly, we have very high CPU utilization, almost 100%, but the real problem is that max worker percent is at 100. So we know what the problem is. Let's see what we can do to fix this. Let's look at query store first. So this is a query that looks at query store runtime statistics in the last 10 minutes. If I do that, I see that there is only a single query running. That's my start procedure. I see that its CPU time is quite high and there's a high number of executions. But what's really interesting is that max DAP is set to 16, which is quite high. So that's the first red flag. Now, next, let's look at wait stats. So we see that our top 10 wait stats, the very like the top three are CX sync wait types and SOS scheduler yield. So SOS scheduler yield shows that we have high CPU utilization as we see, but those two indicate parallelism. Now, if you are used to troubleshooting parallelism, you probably are used to seeing CX packet wait. In Azure SQL, we now have these two additional weights that are similar. So CX packet is still there, but in addition to that, for some types of parallelism, we also have the CX sync port and CX sync consumer. Those are documented. So at this point, parallelism begins to look like our culprit. So let's look at database scope configuration and at how parallelism is configured. So max DAP is set to 0, right? And let's see what is our database service objective. It's a general purpose database with 16 cores. So that really explains it. So we have excessive parallelism happening. And because a query with excessive parallelism could use a lot of workers, that really causes the problem. Now, there is a change in our SQL database where by default for a new database, we no longer set default parallelism to 0. It's actually set to 8 to avoid this very specific problem. So the fix in this case is quite simple. We just reduce parallelism to 4. And we can see that errors have immediately stopped. So that's the end of my demo. And at this point, I will hand it over to Denzil to talk about the remainder of the session. Thank you.
Let's look at the next scenario, which is optimizing CPU utilization. And we're not going to look at it holistically, but just one scenario. I'm Denzil. I'm another program manager, a colleague of Dimitri and Sanjay. So if we look at CPU, if you look at resource consumption or troubleshooting performance on any SQL server, effectively you have two paths you follow. Either the workload is CPU bound or it's waiting on a particular resource. And the waits can be latches, locks, so on and so forth that we are not going to cover right now. In the CPU part, the query or queries can be either executing or compiling, and both of those can consume CPU. And there could be a multitude of reasons, such as bad query plans due to param sniffing, cardinality estimation, some of the constructs in queries such as UDFs and all, consuming more CPU, data type mismatch, so on and so forth. We're not going to go into all those cases. But either way, the flow of troubleshooting is kind of the same. So you look at resource stats and see if the instance or database is consuming a lot of CPU, or can look at the workload group or pool history. Then you find the query or set of queries that are contributing to the CPU. And then there are edge cases where there's spin lock contention, so on and so forth. So the methodology is pretty much the same. So let's move on to a demo. In this demo, I am going to start a workload here. And it'll take about a minute or so to run. And while this is going on, we'll switch to a dashboard. This dashboard is using Telegraph, which is an open source, monitoring, software, if you will. And you'll see in a second the CPU is going to spike. And there are two things you will notice real quick is that the CPU spikes, but batch request doesn't spike. So it's not kind of a lot of queries or load increase per se, right? So batch request is pretty low. You're still at like 2 or 3 or 4 requests per second, but CPU has spiked. And this is not a big machine. It's not a big database. It's just an 8-core database. And so let's look at kind of the query, view of the house. So if you look at resource stats, which is the same thing that the graph is charted on, we see that CPU percentage has increased dramatically, closer to the 90% range. And so what we're going to look at is, query store now to identify those queries. One thing that stands out here is, we have a winner here. So we're looking at top resource consuming queries in the graph in Query Store, and pivoting on because our bottleneck is CPU time total. And though the plan kind of looks pretty good in the sense that there's an index seek and a key lookup, it's not a scan or any big transformation, if you will, no aggregates, no sorts, anything of that sort. The CPU time consumed by this is quite high. So if you look at average CPU time is 23 seconds, and total CPU time is significantly more. So you can go to the query from here, but I've already copied and pasted and formatted it nicely. So from the query perspective, I'm just going to run this. But that query effectively was doing this select on a temp table with a specific predicate. Right, and the temp table. So if you look at this query text, that's effectively what it is. But I just populated the temp table so that we can get an actual plan and compare it to what our estimates is. Because in the estimates, you had just one row being returned. So let's see if that's actually true. So the plan has come back, and if we scroll to that portion of the plan, we see that though estimates are 1, actuals are actually 300,000. Right? And so this nested loop, which may have been efficient for 1, is now doing 300,000 serial seeks. And this is a serial plan. It's not a parallel plan. So there are a couple ways to kind of optimize this. One is instead of a table variable, use a temp table, and this is in the past. So we create that. So we create a temp table. So temp table have stats. And so we'll take a look at the plan real quick once it's done. So a couple of things we see at the onset. Number one, that there is parallelism here. And number two, if you go to the estimates, they are much more accurate. At 300,000. So plan choice kind of determines that. But more importantly now, in the new databases, you get the compatibility level 150 by default. This is, but if you've spawned or created a Azure SQL database in the past, your compatibility level of the database might not be 150. So in 150 compat, this same query, which actually took 23 seconds before, without change. So this is not using the temp table. This is using the table variable itself. Performs significantly faster. So this is 1 second instead of actually 23 seconds, right? And so we intelligently actually at runtime get the right estimates from table variables. So if you look at the estimates here, the estimates are correct. It's 300,000, 300,000, and this took just 1 second. So quickly running through kind of the stress scenario of the fix with compat 150. So if you look at the previous scenario, this took roughly 1 minute or so, or 3 minutes or so. Looking at the stress scenario, this is just a matter of few seconds, right? So 17 to 28. So this is about 11 seconds. Same thing in CPU usage. If I refresh the dashboard, that CPU usage will barely register because it was an extremely short duration of time. I can give it another refresh period, but it never goes over 40 or 50%, and that batch is already done. So that's CPU troubleshooting in a nutshell. We'll look at the next scenario, which is data loading. Data loading on Azure DB has a few things you have to keep in mind. One is that, as Dimitri has mentioned in the past, all Azure databases have some resource limits. The most relevant one for data loading is the log generation rate. So optimizing log generation rate is key to efficient data loading, right? One distinctive thing in Hyperscale is, irrespective of the compute size, the log generation rate is the same. Even for 8 core, you can get 100 Mbps log generation rate. For some of the other tiers, the log generation rate is in some way tied to compute or number of cores. The other thing is, in Azure, in order to give you the 99.99 SLA levels, all the databases are in full recovery model. So that's full logging. So when you're comparing to something from on-prem, ensure, which is in simple recovery model or non-log mode, for some of the bulk inserts, keep that in mind that everything on the Azure SQL DB side is full recovery. So things that help in maximizing this log generation rate are data compression, using column store, or even row store data compression. Using larger batch sizes in some ways, or bulk insert, and then loading transient data into temp DB or memory optimized non-durable tables so that they're not logged. And then indexing things such as loading into heaps is more efficient than loading into a table with a lot of indexes, because you can use tab lock and maximize that log generation rate by having concurrent threads inserting into the heap with tab lock. So let's look at some, a demo. So one more thing actually. Log generation rate is throttled at some point or capped because of RTO, RPO expectations on the Azure SQL DB side, right? It allows us to recover quickly in terms of a crash, when there is a crash. It also avoids throttling so that the replica can be within that RTO or RPO objective. So some of the key weights are listed in this. I'm not going to go through each one of them. Effectively, there are different weights that indicate why log generation rate is throttled. Either you've hit a cap or some sort of replica or is behind in the case of GODR or Hyperscale. Let's look at a demo of maximizing your load throughput. And to start with, we're going to look at a Databricks scenario, if you will. So I have a Databricks notebook here, and have two files that are 4 gigs in size. So there's 8 gigs of data being loaded, or raw data. I'm going to get this started while we actually look at some of the config options. So in this first case, I am loading into a heap. And so because I'm loading into a heap, there are a couple options that come to mind here. One is using table lock to allow concurrent load into a heap. And then I am using a batch size of 100,000 here. So all I do is I'm reading from the lake, data lake, from these two files, and defining a schema on top of it. And then, effectively using the new Spark connector, which is SQL Server.jdb.spark, to bulk insert into SQL. So a couple of things I will see if I go to the dashboard. One is that my log generation rate is close to the max. So we are looking at 100 MB per second, which is the limit of the Hyperscale database. This is a 16 core database. You see the log generation limit is 100 MB. So you will see, if I look at this holistically, that my log write percent is close to 100 here. And so I am going to get throttled on log generation rate. So if I look at my weights, I will see at some point, log rate governor as a big reason for weights. So I'm seeing that effectively weights are waiting on log rate governor. If I switch to a view of the query, I should see the same thing. At the bulk insert level, I see that log rate governor is my primary weight type. And doing diffs or deltas of weight stats. The diffs of the weight stats also show log rate governor as the bottleneck. These are two diffs 14 seconds apart. You see the average wait time is 12 milliseconds. So let's go back to the Spark notebook, and sorry. And this should be done. This took a total of 2.5 minutes. So I'm going to start the next one, which is a bulk insert. The only fundamental difference here is that this is into a clustered column store table. And because of that, you cannot use tab lock equal to true, tab lock equal to false, um, because otherwise it would block, it would serialize the bulk inserts across the threads. And then, you see the batch size I've optimized for the segment size. So I've used close to 1,000,000 rows. That's 1024 times 1024, so that most of that could land into compressed row groups. And the idea behind this is actually, so that we land into compressed row groups. So we are maximizing log generation rate. So to insert the same 8 gigs, we would effectively maximize the log generation rate. So let's go and look at our dashboard again. And we will see in this case, we are not close to the 100 Mbps. It's closer to 70 Mbps log generation rates. Instead of getting throttled here because we hit the peak, we are no longer throttled here. That's one thing. So if we look at weights for the last, I'm going to just switch this to the last 5 minutes. The weights no longer you see log rate governor anywhere close. Instead, it's write log when we're writing to the log, which is fine. We're not at least artificially being throttled, and async network IO. We should also see on average an increase in CPU because going to columns to compress row groups means there's some compression involved. And so we see kind of an increase in CPU. Overall, the time is a little better. So instead of 2 and some minutes, it's 1.67 minutes. But the time is not the main reason. Main thing is optimizing of this log generation rate, and the time difference would be larger if you had a larger Spark cluster. So on and so forth. So last but not the least, of course, column store gives you great query performance and a great amount of compression. The same amount of rows, as you can see here. I will pull these together. These were the rows we just ingested in 2 minutes. So that's around 66 million rows. Took substantially less space. Reserved space on the first one, on the first one, which is column store. This was 6 gigs versus 11 gigs. So that's effectively the loading scenario on column store versus heap. And then on a heap, of course, you would require additional indexes, which would even take further space for querying purposes. Another aspect of load we will look at is kind of bulk inserting from an Azure storage blob. So first thing is, beware of your limits, in particular, as we talked about the, log generation rate. So DM user DB resource governance give you that. So first step, I create a table, not very interesting. And in order to actually bulk insert from blob, I have to create a scoped credential. So I generate a SAS token and I create a master key and a scoped credential. So this is to my data lake of files sitting on lake. The next step is I create a external data source which points to the files that I have on blob. And last but not the least, then once I do that, I can actually bulk insert into a table directly. So I'm going to actually enable actual plan here, and then I will go ahead and bulk insert. So a couple things we'll see with the bulk insert. Number one, this bulk insert is not going to maximize my log generation rate because I have only one thread bulk inserting. So if I look at kind of this log bytes flushed per second, we're going to taper much below kind of the 100 MB per second, which is our log generation rate. right? So we may be close to 29, 30 MB per second, but we're not going to, go to 100 MB per second. It's very difficult with one single thread being executed. Next, let's execute this bulk insert. So when we actually execute the bulk insert, and for simplicity, I've removed the batch size so that we get one plan. I'm looking at the actual plans. If we look at this bulk insert of one file is not going to maximize your log generation rate. And the reason is it's very difficult for one thread to maximize your log generation rate. So you will see this number go up, but it'll be closer to the 20 to 30 MB, range. As you can see, it's plateaued here, and it'll be done in a second. And so it's completed successfully in 22 seconds. But if you look at kind of the plan is a serial plan. So for every single file, we actually use one thread, and it's a remote scan to that file. And more importantly, if we go to the waits aspect of each execution, you are going to see something called this improv IO wait. And this is actually the time where it's reading from blob, right? So, I mean, rather than spending SQL compute, unless it's a ease thing, it is advisable to use an external compute to actually read that files and just stream the data into SQL, so as to remove that improv wait. And again, as we talked about, kind of from a bulk insert perspective at least, there is no maximizing log generation rate with one thread. You would have to go parallel in order to do that. With this, we will wrap up our session. A few other data loading tips, as we talked about in parallel sessions. Column store does require memory grants, in particular if you're going into compressed row groups directly. And so reduce parallel sessions if you're reaching a point where you have memory grant contention. There is a blog that explains that. Load from an external compute engine if possible, and then partition large tables, in particular partition. It's not just about the load, it's about ongoing maintenance, archival, things of that nature when you partition. So load into staging table, build align indexes, and switch into the partition table. Last but not the least, here are a few Azure SQL resources. We have a learning path which guides folks who want to know or learn more about Azure SQL and associated fundamentals. There are SQL workshops and Azure SQL workshops, and some links to documentations and videos. Thank you for attending this session. We look forward to hearing from you if you have any questions. I hope you enjoyed the session. Have a great day.